Greetings, School of Tomorrow. So I think students and teachers alike, I think you've started to see, if you've been watching the last few videos, that the CCP or the IVM can easily be imagined as just a checkerboard of cubes. So it's just like XYZ in some ways, except there's the alternating pattern, you could say, of black and white squares, except we're going to say of has a sphere at the center or not, right? It's alternating. So if this rhombic dodecahedron represents the domain of a sphere in the CCP, then in these 6 directions, in the directions of these half-coupler tips, there will be no sphere right here. This is going to be the center of a neighboring cube, but it's going to be empty. There's no sphere. The sphere that this guy is touching is through the edges of the cube. In other words, the diamond face centers of the rhombic dodecahedron, these are the interfaces, the 12 interfaces to the neighboring balls. And since these short diagonals are all the diagonals of cube, the same cube, we can realize from that this inner cube communicates with its 12 neighbors through the mid-edges of this cube. The mid-edges of this cube are the kissing points of the center sphere here to its neighbors, 12 around 1. So we reveal that the checkerboard of cubes is a perfectly fine way to begin. Now, one way to look at that in codesters here is to see this is where the spheres are limited to the radius of the inner cube. So we're kind of looking at a cross section and we're saying these spheres must be kept small, so we'll have to hold them in place some other way, a la C60, right? I've been assembling some more, show you more what it looks like, work in progress, putting it back together. It's not graphene anymore. Some other molecule, we could call it a molecule. Different namespace, of course, it's made out of plastic. So let's let these balls expand. And this is like expanding to really fill each rhombic dodecahedron this time and actually touch all the neighboring balls. Because you'll notice in the current picture there in the pattern, the 2D pattern in codesters, that none of those balls are actually touching each other. And that's because that's more like C60. C60, not carbon 60, but the brand C60 spelled C number 6XTY. This is, of course, alluding to carbon 60. Sam knows well about carbon 60, so he marketed it in a clever way. So let the spheres expand beyond their inner cubes and actually communicate with their neighbors through the mid-edges of the cubes. Checkerboard, alternating, filled, not filled, right? You get that picture with the cannonballs. We still are going to have trivial in there. We're still going to have a way to slice through it and see the triangles. So this is already what I want to show you. Now I'm going to change the diameter so that they actually touch each other. We'll run it again. I get a fleet of tractors or turtles to run down the field vertically. So those are 12, not 12, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 separate turtles. And then I get them lined up to run across, also in series, one after the other. The loops are in code over here to the left, nothing too special. And then bam, there's my circles. But you could call this a layer of spheres, and now they're actually touching each other. They're intertangent, and they're bigger, and they're talking to each other through the diamond face centers. But we're only seeing like one layer of those, right? This is Squaresville. If you go back a couple videos, you'll see what I'm talking about. What we're doing is limbering up your mind to think in terms of this particular scaffolding that's well known to scientists, nothing alien here. It's called the CCP, IVM, FCC, Octet Truss, very well known. It's how cannonballs and fruits are stacked. It's just we don't spend much time in it in the early grades or academically in the early grades, and so we don't develop much fluency around it. We don't develop the imagination around it, and you could say this is kind of like a branch of Montessori or a branch of Waldorf, kind of. It's one of those early education philosophies that says, hey, we really need to educate the right brain graphical imagination in spatial geometry with an eye towards late 20th century breakthroughs and discoveries. There's always progress. There's always another approach that looks more promising. And in this case, Buckminster Fuller, big influence. Mistake made in bleeping over his stuff. Too quick to dispense with it. I stuck with it, and I have a better curriculum as a result. All right, talk to you soon.